Good morning. Welcome to NPTEL Transfer Phenomena in Bioprocessing course, week 4, lecture 5. So, we discussed last class rotameters, then orifice meter and Venturi meter. So many, this all come with the volumetric flow rate measurement. Today we will discuss about the pressure measurements. So, the previous one we discussed the volumetric flow rate measurement, but this class we can go ahead only for pressure measurement. So, what is the pressure here? The pressure is the force of fluids against the containers of wall. So, the pressure always we write as a pressure equal to F by A. F is the normal surface of force, the F is the force, but then A is the area, force by area. So, that is called a P. The force we always write a Newton, then area we write meter square. So, the pressure units here P we can write P equal to Newton per meter square. What is the force unit? Force unit is a Newton, then the area is the meter square. We always write P equal to F by A. Pressure is equal to the ratio of force by area. So, again the fluid is treated to continuous distribution of matter, like properties like pressure and density, it vary continuously from point to point. Point to point, the pressure and density definitely will vary. So, what are the different units of pressure we are using here? So, pressure normally the SI units we use for 1 Newton per meter square. So 1 into 10 power 5 for atmospheric pressure, 1 into 10 power 5 Newton per meter square. Sometimes we write for the standard pressure here 1.01325 into 10 power 5 Pascal. So, this is another units. So, but SI units we always use the Newton per meter square, 1 point here SIN 01325 into 10 power 5 Newton per meter square. Sometimes we use for English units also, that is a PSIA, that we write for 14.696 PSA. Sometimes many units are there, 760 millimeter mercury, but these are the pressure units, then torr. So, different type of units are there, pressure, here the PSI units, then the meter of water. So, we can give meter of water also, then the feet of water. So many units are there. Then in terms of inches mercury, 29.92 inches mercury also. You convert this one in terms of mercury, then we call 29.92 something inches mercury will come. So, these are the different type of units, but normally we use for the SI units here, pressure is the Newton per meter square, or sometimes we write for kilonewton per meter square. But these other units are English units, some units are atmospheric standards. So, normally we write 1 atm equal to this much value. So, that also on another pressure units here. So, the pressure in the fluid to calculate, so this is necessary for the derivation here. We already discussed here m equal to rho v. What is m? M is the mass. Mass is the kg. We write. Then density is the kg per meter cube. Then volume is the meter cube. So, get cancelled. Then we get mass. So, the mass is the rho h2a. We can write the other way also. The rho is again density. We call it as a density. Density kg per meter cube. Then height of the column or height of this liquid meter, then area meter square, again we get kg, that is also mass into kg. So, we already discussed in the Newton's second law, F equal to m into g. M is the mass and then g is the gravitational. So, gravitational acceleration. So, the mass, how to write mass here? Mass we can write rho h2a, rho h a. The rho is the density, then h is the height of that one, then area into g. So, we know this one rho h a g, we write a f. But what is the unit of pressure unit? F by a equal to p. So, divided by a, both cancel, then we get rho h g. So, this is another the pressure units. So, we always write rho g h. If its density varies, then we write delta g. Here delta g, if it is head is varying, then we always write a delta H. Of course, the G is a constant, so G we cannot write that one. Rest of things are, so if you write delta here, then automatically delta pressure, there is a pressure drop also here. So, simple figure shown here, and you assume there is a P naught, that is the initial pressure, P naught pressure. So, the corresponding the area we write A naught. The pressure is a P naught, then the corresponding area is a A naught. Same way the pressure P1 acting here, the P1 that corresponding that this area we called as a A1. But sometimes if a uniform cross section area, then no need to this one. But if it areas are different, then definitely the A1 also should be a different. So, at point 2, these are point 1 location and the 0 starting point, then point 2 location. Point 2 location again wherever the pressure is there, that we called as a P2 and the area is a A2. So, if I want to here, so assume 0, 0 to the 1 we called as a H1, the height of the first one. Same way for if it start from 1 to 2, that height is the H3, but the overall height is H2 equal to the H1 plus H3, the summation of both H1 H2. So, if it pressure in the static fluid, not in the moving this one, if it is pressure in the static fluid, then how this one. So, now then we discuss a P equal to H rho G, then how we derive this using Newton's second law. We will move to another slides. Now, then pressure same way from that figure, when you calculate total absolute pressure P2. So, the first go to P2, where is the P2? P2 here. The P2 equal to rho G H2 plus P naught, because the rho G H2 whatever this one, the acting that one, then P naught is the initial pressure, that initial of this one. So, I will show you maybe this is a P naught, then whatever the total height of that one H2, rho H2, then that's the value is a P2. So, P2 equal to, we can write P2 equal to rho G H2 minus of P naught. Same way for P1, what is the pressure of this one, then pressure also we are writing rho G H1 plus P naught. So, that is the pressure to P2, then the P1 is here. So, the difference between P2 minus P1, automatically the P naught will get cancelled. The P naught will get cancelled. So, then we get the P2 minus P1 equal to rho G of H2 minus H1. That is a delta P. So, we write delta P. So, the differential pressure here, the pressure difference between any two vertical heights, any height you can take H1 to H2 by subtracting these 2 points. So, here rho, then G, the delta H. Since the height is varying, we are writing delta H. Sometime if gravitational varying, then we can always write a delta G. So, delta G, delta H, the based on the equation we can always change, but when you have delta rho, okay. So, then if it delta rho varying, then automatically the pressure drop also vary, delta P also vary here, okay. So, then what is the head of the fluid here? The pressure is commonly expressed in terms of head, but the unit is meter, or sometime we write feet. So, that is the unit, different units, SI units meter, then the English unit is a feet. So, different type of units are here. What is head? Head is the actual height of the column of the liquid, we write a head. So, head is only determined by the height of the liquid, whereas the height is there, the height we always write the head of the liquid, height of the liquid. As a vessel containing the liquid can be any size, any shape, does not matter, but for height here. So, the height how we write here, the P equal to H rho G, this is a pressure equation. So, H we can write P by rho G. So, that is only height of the actual height of the any column liquid or head of that one. So, the ratio of P by rho G, the unit is meter, because already pressure units and the density, gravitational, finally we get only meter. So, the head is here, we can always write P by rho G. So, then we always use for manometer, that is a pressure measuring device. So, manometer device measure the pressure using the liquid filled tube. So, whenever the fluid is under pressure, it is allowed to push against the liquid in the tube. So, there is a movement happening here. So, there is a movement of the liquid is proportional to the pressure. It measures the differential pressure, differential delta P, indicating the difference between two pressure by the shift in the liquid column height. So, basically it measures the delta P, the manometer measures the pressure drop, and that is a differential pressure of P2 minus P1 or P3 minus P2, basically the difference between 2 points. So, normally water is used, commonly use the liquid in the manometer, normally they will use here. So, what are the different type of manometers here? So, one is the simple U-tube manometer, then there is a two fluid U-tube manometer is there, then inverted U-tube manometer is there. So, these are the three type of manometers are available. So, the simple U-tube manometer here, so a simple U-tube manometer determines the same pressure difference between the 2 points. You want to measure P1, P2 or different points, you want to measure by balancing the hydrostatic pressure of the two immersible fluids. So, here the A and B not mixing, A is immersible with B. So, here assume that is a, then the A called density of A, the fluid A is the density of A. Same here the fluid B, and then the density of B rho B. So, up to this the density of liquid is the rho A, the both fluids are immersible. So, this is a very transparent U-tube, we can see this one, the filled with a heavy immersible manometer like mercury or water, that is a fluid A. The fluid A we called as a, then the density automatically rho A, density of this one rho A, the units are kg per meter cube. Same way for other one, it is a filled with a lighter process fluid, that is a light density this one. So, that is only its upper hand. So, that is called rho B is the density of fluid, and again that of same unit kg per meter cube. So, here the A and point 1 and 2, the pressure is same with respect to position. So, somebody asked what is the pressure here, and 2 and the 3 both point the pressure is same, but pressure vary with respect to height, not vary with respect to the horizontal place. So, the pressure P2 should be the same and the P3. So, PA is the pressure at the point 1. So, that is a point 1 is there. Where is the point 1? That is the pressure is the PA. There is a point 5. There is a pressure point B, PB. So, PB at point 5. The pressure at point 2 we write P2 equal to PA. PA is the what starting point PA. I will go back. I will show you. This is a PA. Then Z plus R rho BG, that point is the P2 is the PA plus Z plus R rho BG. So, the R is the reading of manometer, reading the manometer meter. Same way point 2 and 3 the same height horizontal plane, because already I discussed there is a P3 equal to P2, both are same, because the height of that both is same, whenever the pressure vary only with respect to height. So, P3 is the P2, both are same, then we can write point P3 equal to P3, we write PB plus Z of rho BG same or rho AG. So, then you equate the 1 and 3 equation, you equate the 1 and 3, then finally we get the equation of pressure drop, we write pressure drop delta P equal to R into this one. So, this is a delta rho, the density of A and B. A is the more density compared to B than the G is here. Sometimes R also vary, that we write for delta H. So, here only variable is either R or rho, not G. G is always constant, but if it vary R, then automatically the pressure drop also vary. So, the delta P is the function of only for here R and rho, that is the height here, because G is almost constant. So, only this only vary here. So, what about the two fluid U-tube manometer? If it two fluids here, its manometer is a sensitive the modification to the measure, especially small, very small pressure drop. The pressure drop is very, very small. So, then we can use for the delta P. Delta P is a PA minus PB. So, there is two large reservoirs, the cross sectional area A the top of that one, this one A is a capital, the A, that's the top of the vertical limb. Same way the lower portion of U tube, and then that cross sectional area is the small a. The cross sectional area is the small a, and again there are saying that the rho A is the density of heavier fluid, whatever the rho A, and this is density heavier compared to rho B. The rho B is again is also, both are immiscible, but is very lighter. The density is lighter here, then the rho A density is very high. So rho A is always very high compared to rho B, and the area is the top is capital A, and whenever the small this one, then small cross sectional area is a small a. We denote like this. So then again, for proceeding making pressure balance, then finally we can write PA minus PB equal to R minus R naught, then rho A minus rho B. A is the cross sectional area of the smaller one, and A is the capital area. Same way here, density of B, rho G. Then what do you mean R naught here? R naught is the reading is when PA equal to wherever PA equal to PB, then that R naught is here. Okay, this is a two fluid U tube manometer. Then the next one is for inverted U tube manometer. What is inverted U tube manometer? You just make it a reverse. So inverted upside down, and again the height of the H1 here, and the same way for H1, H2, the different height here, and they say lighter fluid immiscible density rho B, then but the rho A is the lower limbs directly connected to the liquid line being measured the rho A. This is a rho A, density of rho A, so directly connected to the line of that one. So it's definitely very useful for the measure the small pressure difference. Wherever the pressure difference delta P so small. If delta P higher, maybe it's not this one. Whenever the pressure difference small, and definitely this inverted U tube manometer is very useful to measure in pipeline. Sometimes without requiring heavy toxic liquid like mercury, no need, we can measure, even though we can without this one, we can measure the pressure drop. So that's called inverted U tube manometer. So reverse that one. So next is the piezometer. Piezometer is the simplest form manometer. This is consisting as a single then transparent vertical tube. So piezometer is one of the where one end is attached to the wall. The one end is attached. This is attached to the wall, but other one is the vessel containing liquid at rest in the motion. But what about other end? Other end is the open end. So piezometer is open to the atmosphere. So you can see here that the rho is the density of fluid here, because whatever we rho use, that's the density of fluid. Then the G here, G is the acceleration of due to the gravity. What is the acceleration due to gravity here? So the H is the rise of the liquid. What is the H? How much? Because this is directly connected to the pipeline. So how much getting rise of the liquid? So that directly we can get the value of H. H is the height of the head of the fluids. So we can get directly. So the liquid rises in the tube under action if the internal pressure until it reaches a column height H that perfectly balance the fluid pressure. So it give exact value of this one. So this is one type of pressure measurement is called a piezometer. So then you want to measure the absolute pressure and gauge pressure or the taping point is calculated directly to the from the vertical same figure I have shown here, the fluid height here head. So there is a P equal to rho G H is a gauge pressure, P equal to rho G H gauge pressure, but I want to get absolute pressure, then add gauge pressure, then atmospheric pressure. So then we will get the absolute pressure. You want to get the absolute pressure, then add the gauge pressure, then atmospheric pressure. So both if we add it, then we will get the absolute pressure here. Other is a Bourdon pressure gauge. It's a, you can see here the figure is already here. So one is applied pressure, and then this is a pointer, and then is a piece of So tube is containing the boron tube. We always say the boron tube here. This is a boron tube here. Is a durable. It's a mechanical pressure measure device. Uses the elastic deformation. It's a curved. It's look like curved. Then flattened metal tube. Open at one end. One end is open. This side is open. Then other end what happened? It's exposed to the fluid. So other is the closed to other end. Other end is the closed to estimate the pressure. So when subject to internal fluid pressure, whenever the tube becomes mechanically stretched, spontaneously straighten out. When you increase that one, then automatically the mechanically it goes to straight. So if I want to measure the degree of the tube straightening, so whatever this one, so it's a curve, no, the curve structure this one, then it will try to move straight. So then the degree of the tube, this one tube straightening is a directly proportional to the pressure difference. That's a very important. So this is a directly proportional to the pressure difference. So between the inside the liquid, then outside the other tube. This is the inside, then it is connected to outside the tube. Even the slide movement is controlled by the geared sector here. Geared sector mechanism is there, which moves point to the calibrated this one. So this we call as a boron gauge pressure. So we will always use to measure the pressure measurement. So next is the problem 1. We will see it's a very simple problem. There is a manometer is being used to measure the differential head. That's the value of H value or pressure drop across the flow meters. The heavier fluid, that is a mercury, the heavier fluid is a mercury of density of mercury with a density 13.6 gram per centimeter cube. So convert in terms of kg per meter cube, then 13,600 kg per meter cube, 13,600 kg per meter cube. Then the top, the fluid water is the density of water. The density of water is again they are giving 1 gram per centimeter cube. You convert in terms of 1000 kg per meter cube. Then the reading of the manometer, R value is already given, R equal to 25 centimeter, the value is R equal to 25 centimeter. You convert in terms of SI units. The density of mercury you convert of SI units. Then again water also we converted as the SI unit. Then the mercury level 0.250 meter. So there is a gravity we have to add, that is a gravitational this one 9.81 meter per second square. So it's like acceleration due to gravity. So now everything you know that one, we know the formula. So from this one, because we already derived P equal to F by A, then the F you can write mg, m into g. So m how to write? M is the H rho A g, then divided by A. So we can write here, because the height is the meter, then this also meter square, then we will get a, both will get cancel, then finally we get a H rho g. That is the pressure of the this one. So here pressure drop is here, the density of mercury, then density of water. Density of mercury already we calculated, we know that one, density of mercury is the 13,600, then water always close to 1000 values. These are the in terms of kg per meter cube and SI units, these are SI units. So once you know that one, we got a value of 12,600, the density difference itself. Then if pressure drop, you calculate pressure drop, because we know this value, then the G is the 9.81 meter per second square. Then there is a manometer reading, the problem itself already given, the manometer reading here R value. R value is the 25 centimeter, convert in terms of meter. So the final answer is the delta P equal to 3.09 to 10 power 4 Newton per meter square. So there is a pressure drop across the flow meter, we write this way, the pressure difference correspond to the head loss across the flow meter, that also can be used to estimate the flow rate when the flow meter calibration, if you know that one. So from there we calculate the pressure drop, that is the pressure drop value. So this is a way to measure the pressure. So we started with volumetric flow rate measurement, like we started orifice meter, venturi meter, then pitot tube, rotameter, then these all will use for volumetric flow rate measurement, but this one the pressure measurement. So, this is also done. Thank you.